So we are going to shift gears and we are going to look at a very popular supervised learning algorithm, right, or supervised learning model I should say, because there are many different algorithms for estimating this model are based on decision trees, right. Can people at the back hear me? Fine, okay. So decision trees have a very very special place in all this machine learning stuff, in that they are very widely used, right, and very poorly understood. No, in terms of we talked about all this bias, variance, trade-off, classification error, we can show convergence, we can show approximations and a whole bunch of other things for all the linear classifiers, linear regressors, right. We know a lot about all the linear stuff, right, and some of the non-linear stuff like SVMs and so on and so forth, again we have very strong theory, we know about convergence and things like that, right. With decision trees I can tell you what the problem is and I can tell you what is the best known heuristic for solving the problem, but I can't even tell you how good the heuristic is, right, because there are isolated results under very special conditions. People have some results on how good the heuristic is, there is this best possible tree that you can learn, right, and how close would it get you to the best possible tree, right. So there are some very isolated results, right, but there is nothing that is really something out there that we understand well, right, and it is incredible because it is such a simple idea, it is a very simple classifier, right. So it is more or less along the lines of how humans do their decision making, right. So when you are trying to decide whether something belongs to some category X or some category Y, right, how would you think you go about doing it, right. You don't create a hyperplane in your head, right. Right. So typically what you end up doing is, okay, is this red? Okay, it's not red. Okay, is it round? Oh yeah, it looks round and okay, it's blue. Maybe it's that, right. Essentially what you are doing is querying some properties of the object, right, or some properties of the entity at hand, right. Do I want do I think he is a studious boy or not, right. Then I can ask all kinds of queries. Okay, does he show up for all the classes, right? Does he sit in the first row all the time, okay? Is he smiling after quiz 1? Right. So I can ask, I can build these things, right? I can ask this series of queries, right, and then I can essentially I am building some kind of a characterization of the object, and then I say, okay, great, so this person is class 1, okay, this person is class 2, right, so on and so forth. That is the whole idea behind decision trees, right. You are essentially trying to, if you think about what you are doing, you are trying to partition the input space into certain regions, okay, right. The feature 1 has value X, feature 2 has value Y, feature 3 has value Z, and that gives me some region in state space. So what do I mean by that? Let us take a right. So the first question, let us say a 2-dimensional data set. Now let us forget about all the relevance to real life and things like this. So I have 2 variables x1 and x2. Now I am going to ask the question, first question, here is a new data point, is the x1 of this data point greater than 0.6 or lesser than 0.6? Okay, that is the first question I ask. So what am I doing in some sense? I am, right. So I am splitting this into 2 parts. If it is greater than 0.6 it will be here, if it is lesser than 0.6 it will be here, right. Next question I can ask is, okay, suppose x1 is greater than 0.6, okay, then is x2 greater than 0.2 or not, right. Then what do I do, right. So this region is now x1 lesser than 0.6, x2 greater than x1 greater than 0.6, x2 greater than 0.2, and likewise this is x2 lesser than 0.2, and likewise here I can ask the question is, what kind of question can I ask here? Come on, just say something random. Don't think too much about it. Huh? Huh?
We can
Greater than 0.7.
make any conditions on x1 and then cascade it with x2, x1.
You can do anything, right? So typically they alternate, but you can also ask a question, okay, is x1, given that x1 is less than 0.6, is it less than 0.3 or not? Or you could ask, is x2 greater than, don't give me some root 2 or something, but 0.5, okay, good, right? So okay, as soon as I write that thing there, it becomes 0.5.
So what if the regions that will characterize each class aren't rectangular but have some but like form some linear function and are like say slanting boxes or anything?
Can I come to that a little later, right? So I am just trying to mimic the way we try to think of things, right? So normally what this is, all of you were agreeing with me when I said, okay, you will think about attributes one at a time, right? So is the price okay, is the TV screen of the right size, then I am going to buy or not, right? So like that. So I am just mimicking that process here, okay, then we will come to other things a little later, right? So I mean, it will be really truly amazing if your true class labels are going to lie like this, right? What is the problem, what do you think is the likelihood that the class labels will actually be this kind of rectangular regions?
More discrete.
Huh?
Discrete cluster.
It could be high, I mean it depends on what process was used to generate the class labels. If the labels were generated by doing this kind of region splitting, obviously you have to find the right regions, but we are making some kind of an assumption, right? Earlier when we made assumptions about linear, right, we are making some kind of an assumption about what the boundaries would be, right? Likewise we are making assumptions here that there will be rectangles, right? So if you do not want to make the assumption that there will be rectangles, then it is going to be little harder, right? So not only are these rectangles, right, there is something more special about these rectangles. I mean they are all recursively generated, right? It is not like I can't just take some arbitrary set of rectangles and tile the space, right? They are recursively generated by first splitting it into 2 and then splitting each section into 2 and so on and so forth, right? It turns out right. So this kind of recursive splitting is what is most tractable to handle, right? And for most of our decision tree discussion we will stick with this, right? I will come back and address that issue little later, right, about having more complex boundaries, but almost all decision tree algorithms, right, all the approximations that we do for decision trees use this kind of recursive splitting of regions, right?
Can we use nested rectangles?
Like
one inside the other.
like that. How will you describe this region?
Given x1 is greater.
It becomes harder, right? See, now each of these regions I can describe very easily, right, but if I start doing nested rectangles, right, it becomes a little tricky to describe the outer region, right. I can do something like this provided I am willing to accept that, right, not so it is no longer a nested, really no longer nested rectangle because I had to actually fragment the outer region.
Now you can say is x1 in this range and x2 is in this range. Given x1.
That will give you the inner rectangle, but the outer rectangle you have to actually exclude it, right. I have to specify the outer rectangle and then say okay remove the inner rectangle, so it becomes a little harder to specify, right.
The outer region can be done in union of other rectangles.
What's that?
Union of
Yeah, it becomes harder, right. I wanted to be easy, I want to represent this as a tree, but then the way you are going it make it harder and harder. So the biggest advantage of decision trees is the interpretability. So for example, this tree that I have, this region segmentation that I have drawn, I can represent it as I have been talking to you about trees, right, where is the tree, right, this segmentation I have, right, I can represent it as a tree. So what I will do is I will first ask the question, is x1 less than 0.6, right, then if you say yes I will go left, then I will ask the question is right. So I can very compactly represent this rectangular segmentation as a tree, right. You can see what is here. I am asking the question, is x1 less than 0.6? If it is true, I go to the right, and then again I ask the question, is x2 less than 0.5? It is true, I go to the right, and I say that this R1, right. So I am essentially here, right, otherwise I am here. Then going to the other branch, right, which is x1 is greater than or equal to 0.6, I am this side, and if it is less than 0.2 I am in R3, if it is greater than 0.2 I am in R4, right. So I can very compactly describe this segmentation as a tree, right. So what is nice about this tree, it is easily understandable, right. You show somebody, okay, so you are building your this, you go out, you become a data scientist or a data analyst or whatever, okay, some manager who makes like 10 times what you do, but who has never heard of a hyperplane in his life, right, comes and asks you for to build a classifier. Here is the data, build a classifier, and then you tell him, okay, I built this classifier and this new customer you should label him as a buyer. Then he will ask you why, right. So at that point you just talk to him about optimal separating hyperplanes and show him something, okay. Well, then the next day probably the manager is going to be earning infinitely more than you, right. So what you should okay, so what you should be doing is showing him a decision tree, right, because that people can understand, right, people even with an MBA can understand, right. So you can see what is my recommendation to you guys after you finish your BTech or anything, right, don't do a MBA, but anyway, so that is easily interpretable, right. You say, oh, that is, oh yeah, you should classify him as a buyer because, well, this on this parameter he is so much, on that parameter he is less, blah blah, and then there you go, right. The biggest advantage of decision trees is the interpretability. It is always easy to explain the decision tree to people. In fact, so much so that at one point when neural networks were at their peak, you know what is the biggest problem with neural networks?
It's complex.
Huh? No, the opposite of decision trees, incomprehensibility, right. This is interpretable and neural networks are incomprehensible. Essentially you say, okay, here is a black box, I do not even know what hyperplane it is learning, right. I mean, forget, if you think optimal separating hyperplanes are hard, I can't even visualize what the neural network is learning, right. So you say, here is a black box, you throw in all your data at one end, something will come out at the other end, you just take it on faith, right. Right, so welcome to the church of neural networks, right. So that's essentially how neural networks were working. So when the neural networks were at their peak, there was this whole line of research where people took a neural network, right, that was trained on your training data, etc., and then tried to construct a decision tree that will give the same decisions as the neural network, will give the same class labels as the neural network, so that you can actually understand what is happening. Okay, it sounds weird, right? But remember that now I am no longer using whatever other heuristic I had for constructing the decision tree. I am using a decision tree which mimics the neural network. So if the neural network learned some complex function of the data, right, I am trying to build a decision tree that mimics the complex function, right. So it's a different decision tree that I would come up with than the one I would have constructed if I had used any of my decision tree learning heuristics on the data from the beginning. Okay, so there is value to doing this, right. Right, so people do see that, right, there is value to doing this, right, because neural networks do something I can't understand, right, but they seem to work, right, they give me a wonderful answer and I do not know what that answer means. So can I use something for which I know what the meaning is and try to understand it in terms of that, right. So that is how useful decision trees are, right, even if you have a more complex learning mechanism at hand, okay, sometimes for interpretability's sake, so you can use decision trees, right. How expressive are decision trees? right. If you remember, we had this discussion about neural networks. I said if you have 2 layers of weights, that is 3 layers of neurons, right, you can basically represent any Boolean function, right. I just, the branching factor might be very high, but then you can represent any Boolean function. So neural networks are universal approximators in that sense, right. So what about decision trees? Right, you can be an universal approximator as well, right. I can just keep dividing and subdividing this space, okay. It's just that my tree might become very large, right. As long as there is some kind of guarantee on the function, yeah.
Does it mean that you can repeat some variable?
Yeah, I can repeat some variables, yeah, that's fine, yeah.
So in this case you can.
Yeah, I could do that. Yeah, I mean, in fact, yeah, he was pointing out in the beginning. I could have as well drawn another line here. Yeah.
No, as in like one more line that lies just within one of those boxes, not through and.
That's okay. Wait, that the discussion was when we were discussing about this line versus that line. Yeah, sure. I can keep doing this if that's your question, right? Now this becomes a much more complex tree, right? So now I'm splitting here once more, right? I'll have another branch here, I'll have another branch here, and another branch somewhere there, right? So it keeps becoming more and more complex. But the point is, conceptually, you can represent anything, right? So it is powerful in the sense that it's a universal approximator, right? And it's just that the number of parameters can grow unbounded, okay? And that's another thing, nice thing about it. It is non-parametric. Remember, we talked about what non-parametric means, right? So decision trees are actually non-parametric. It can just keep growing, right? You can keep adding parameters as you go along.